remember to record before I started lecturing. Heyo. Okay, so today we're going to continue talking about problem solving, but first we're going to make a brief little segue into reasoning for a bit. And the reason why we're doing this is because the term reasoning, it's often used pretty interchangeably with the term thinking. And there's quite a good deal of overlap between the relationship between our thinking, our reasoning, and our problem solving abilities. And so for the psychologists who do want to differentiate between reasoning and thinking as sort of two separate entities or two separate processes, they see it as thinking sort of being this larger umbrella term that reasoning then falls under. So reasoning being a special case or a subtype of thinking. And so when cognitive psychologists use the word reasoning, they often mean a specific kind of thinking. So this is the kind of thinking that is done when solving certain kinds of puzzles or mysteries. And reasoning is a kind of thinking that often involves logic. And so we're going to talk about logic just very briefly. I know that your book goes into quite a bit of detail about, categorical syllogisms and, if-then statements and things like that. And I don't want us to kind of get bogged down in those details. If this was a philosophy class, then we would definitely be getting into the nitty-gritty. But just rather want us to have a more general understanding of logic and the way that logic operates. So there's a video that I'll show in a little bit that will walk us through some of that. But anyway, just wanted to point out that that reasoning involves these logical sorts of rules. And reasoning also involves some other elements as well that kind of sets it apart as its own specific category of thinking. And so when we are reasoning, we typically have one or more very particular specific goals in mind. And this means that our thinking has to be focused. And reasoning also involves us making inferences or conclusions that we draw from other information in order to try to reason through the problem that we're faced with. Some of the conclusions that we draw, or these inferences that we make, sometimes they involve new information. But however, most of the time, the sort of just snap decisions and assumptions that we make are just so routine that we might not notice that we had to do any sort of mental work to get to that point. So as an example of this, let's say that your friend is super into like the intramural softball team. And she tells you, last night at softball, I managed to catch a pop fly. And so from this, even if you're not really all that familiar with the ins and outs of softball, from this, you almost automatically infer that your friend, in fact, did try to catch the ball. Her word managed presupposes that she made an effort to catch the ball. It wasn't like she was sitting there, in far right field with her glove out, just staring at the sky and the clouds, and suddenly the ball dropped into it. No, we automatically assume that she was very active in this process. And so, in fact, we took this statement of, oh, I managed to catch a pop fly, and we draw that conclusion based on our understanding of the words that were used in that phrasing, and the underlying meaning and underlying assumption we have of those words, such as managed. That word it's a more active sort of a word. It suggests to us that somebody put in effort. It wasn't just through a series of lucky mistakes or something like that. And so to study the specific ways that people go about reasoning, psychologists often use logical puzzles in order to try to research this and better understand it. And so in these kinds of tasks, the inferences that people draw, they often follow principles of formal logic. And so this has led some psychologists to develop the idea that there has to be some set of logical principles that we as people really rely on when we are drawing inferences. So there has to be some sort of general pattern of thinking, general strategies that we tend to use in order to make these really quick inferences and to draw these conclusions that we do. However, some other psychologists have noted that some situations require inferences that don't allow for the application of any sort of logical rule. So for example, consider the following analogy. So this is a reasoning task, okay? So Washington is to 1 as Jefferson is to what? Washington is to 1 as Jefferson is to what? Anybody have any guesses?
3.
Okay, and what makes you say that, Taylor?
I was thinking the order of presidents, because George Washington was the first president, Thomas Jefferson was the third.
Yeah, great. So that's one way that you could go about solving that. So there are other ways that you can go about solving that. Another popular one that people tend to think of, which is probably not very popular now, is that the fact that Washington is on the $1 bill and Thomas Jefferson is on the $2 bill. If you didn't know that, there's your fun trivia fact for the day. Thomas Jefferson is on the $2 bill. And that might even be a fun fact for you that the $2 bill even exists. It is a real thing. They're very rare. Honestly, I don't know why they are still in circulation, but you know, that is far outside of my pay grade. But anyway, so there in this sort of example, the reason why I bring it up is there are some problems in which rules of logic don't always apply. And by that, I mean, it's not always that there's going to be the use of a rule that leads you to the right answer. Sometimes there are other rules that can be used to also get you to a different answer. And so we're going to talk about sort of these two different approaches to reasoning that people do. And so the distinctions are what's called deductive reasoning and inductive reasoning. So one way to think about the differences that exist between these two types of reasoning is to look at some different elements of the two. And so for deductive reasoning, sort of at its core, this is the reasoning that we use when we go from the more general to the more specific or the more particular. So for example, going from general to specific, deductive reasoning task or sort of example could be all college students like pizza. Terry is a college student, therefore Terry likes pizza. And inductive reasoning is essentially the opposite of this. And inductive reasoning is where you go from a specific example and you essentially extrapolate or apply it out in a more general sort of a way. So an example of inductive reasoning is that Brian is a college student. Brian lives in a dorm. Therefore, all college students live in dorms. Now, like we're going to talk about, you might realize that there are some problems that we can run into with the way that we apply these ways of reasoning. And so with deductive reasoning, there isn't any new information that is added in during our process of reasoning. So when we take that kind of approach, any conclusion that has been drawn in that process, it represents information that was already given to us in the problem that we're trying to solve. Whereas inductive reasoning, in contrast, can result in conclusions that actually do have new information. And so this can allow us to really react in different ways based on the inclusion of this new information. And another way to go about the differences between these two forms of reasoning is it has to do with the claims that can be made for the kinds of conclusions that are drawn from them. So with deductive reasoning, if you perform it correctly, that is, you have the right information and you're acting on it, you're following the rules of logic, then you can have conclusions that have what are called deductive validity. That is, you can come to an endpoint that you can say, yes, that is a valid answer to have arrived at. That is correct in that you followed all of the rules of logic and the progression of things properly. And so an argument is considered deductively valid if and only if it's impossible for the premises to be true and the conclusions to be false. So with deductive reasoning, it's valid if there is this agreement between the premise or the premises and the conclusion or conclusions. So deductive validity, then, it gives us a really nice guarantee. As long as you start with true, conditions or premises, and you go about reasoning based on logical principles, then the conclusion you come to, it can't be false, right? You can't be wrong at the end of the day. So going back to the example I gave about Terry and the pizza, that argument is a deductive argument, because if it is true that all college students like pizza, again, we're thinking hypothetically, but if it is true that all college students like pizza, and if Terry is a college student, then because both of those conditions, when they are true, then we can know with absolute certainty that Terry is going to like pizza. So it'd be really nice if all the reasoning that we did, it resulted in these really guaranteed kind of conclusions, this sort of, your money back guarantee. But deductive validity, this certainty that we have, it only is the case when deductive reasoning is used. And many kinds of reasoning that we have to use are inductive rather than deductive. And in these cases of inductive reasoning, we actually can't be 100% ironclad certain of the conclusions that we come to. We can only have either a stronger or a weaker confidence in them. So if we go back to the statement about Brian and college students in dorm rooms. So Brian is a college student. Brian lives in a dorm. Therefore, all college students live in dorms. So even if Brian is a college student and does live in a dorm, right, those two premises, those could be true, it doesn't give us a guarantee that the conclusion that we come to from that line of reasoning, that is, well, all college students live in dorms, is going to always be the case, right? We know that college students can live in a number of places outside of just dorms. So in general, inductive reasoning deals with a probable truth. So it doesn't give us a guaranteed truth, but it gives us a truth that we have a potentially higher likelihood of feeling like it's accurate. So if we assume that inductive reasoning, if an instance in which we're using inductive reasoning, it does have true premises and it did follow logical principles properly, it has what's called the property of inductive strength. And so an argument is thought to have inductive strength if it is improbable, so highly unlikely, but not impossible, because we can't rule anything out with 100% certainty in inductive reasoning, for the premises to be true and for the conclusion to be false. Now, if you feel like you got a little bit lost in the weeds as I was going over that, I have a video that hopefully will help make sense of not only the differences between these two categories of reasoning, but also I hope will help make your textbook section about reasoning and deductive and inductive reasoning make a little bit more sense when we're talking about reasoning in the context of cognitive psychology. Okay. All right, hold please while I switch over. Okay. Oh, I can't remember if I shared my sound. I did. Good. Okay. Sorry for the hold up, everyone. Okay.
The psychology of reasoning is a branch of cognitive psychology that studies the way in which humans use logic to come to conclusions based on available information. But not all reasoning is valid, and people may use invalid reasoning to come to illogical conclusions. So just how logical are we as humans? And for that matter, how logical are you? A logic test developed by Peter Watson in 1963 revolutionised the field of reasoning. This classic selection task features cards with letters on one side and numbers on the other side. Subjects are then presented with 4 cards and a rule. If a card has a vowel on one side, it must have an even number on the other side. And the task is this: which card or cards must be turned over in order to determine whether or not the rule has been followed. So basically, you must turn over cards which can guarantee whether this rule is true or false. I'll give you a few seconds if you want to pause the video and think about it before revealing the answer.
All right, so does anybody have any ideas how they might go about trying to solve this? Is everybody quiet because they're afraid I'm showing you something that's going to make you feel or look dumb?
We could turn over the A and the 2 to check to see if there's an even number behind the A, since that's a vowel. And then the 2 is an even number, so you'd want to check to see if there's a vowel on that side.
Okay. Do people agree with Taylor? Does anyone have a different thought?
I would say turn over the A and the 7, but I guess still, like, we wouldn't know for sure.
Okay, well, what are you thinking? What's that guess?
I was thinking that if we turn over the A, we see if there is an even number on that side, and we turn over the 7 to see if it's a consonant. And
Okay.
then I guess it would hold up that way, but we still don't know because we don't know what's on the other side of the K or the 2.
To kind of prove the rule, couldn't you turn over any combination of 2 cards? And then, like, besides undoing all 4 of them?
Besides just not trusting the experimenter at all and just saying, I'm just going to turn all of them over.
Yeah, because if you did the A and the 2, that would prove the vowel, which then we assume that the consonants and the odd numbers match up. You could do the A and the K. Like, you could do any 2 and it would theoretically prove it, but I don't know if that, you would have to trust that the rest of them match the same pattern.
Yeah. All right. Well, these are all really good ideas, and the rationale behind the ideas too. So let's go ahead and watch the rest of the video and see what the results of the study were.
Okay, the correct answer is this. The cards which must be turned over are A and 7. These are the 2 cards which must be turned over to assess whether or not the rule has been followed. Various studies have shown extremely poor results for tasks like this, in which only 4% of participants get the correct answer, the most common wrong answer being A and 2. This can possibly be explained by confirmation bias. The rule mentions both a vowel and an even number, so it may seem logical to choose the vowel and the even number cards. While this may seem logical, as I will demonstrate, it's actually fundamentally illogical. I'll now go through each card and explain why you do or do not need to turn each card over. The key to this task is that you need to understand that you must try to falsify the rule, not confirm it. So the first card A, this is the most obvious, and virtually all participants correctly conclude that this card must be turned over. Because of course, if there's an odd number on the opposite side, the rule has been broken. Now the next card, the K card, this is basically an irrelevant card, which cannot give us any information. If we turn it over and it's an odd number, that's fine. If we turn it over and that's an even number, that's also fine. So if neither outcome breaks the rule, there's no need to turn the card over. The 2 card is where things get tricky and where most participants slip up. If we read the rule again, if a card has a vowel on one side, it must have an even number on the other side. Now, what's important to realise is that this rule only goes one way. Therefore, we cannot conclude that if there's an even number on one side, there must be a vowel on the other side. This is not the case. If we turn over the 2 card and there's a consonant on the other side, that's fine. This does not break the rule. And obviously if we turn the card over and there's a vowel, this also doesn't break the rule. So again, if neither outcome can break the rule, then we cannot obtain any relevant information from this card, and therefore there's no need to turn it over. Finally, the 7 card. This card must be turned over. Why? To make sure there is not a vowel on the other side. If there is, this breaks the rule because the card has a vowel on one side and an odd number on the other side. So looking at both potential outcomes of all 4 cards, we can see that there are only 2 ways in which the rule can be broken, and therefore these 2 and only these 2 cards must be turned over. This rule is...
Sorry, there's an ad because it's a longer video.
I need to find the best way to learn math and science.
It's brilliant.
Whoa.
Here's a new way to learn math.
Oh no, now my screen is frozen.
Math?
No, I don't want to learn how to be better at math. I think I'm past the point of no return on that. Okay. Sorry everyone for the interruption.
This rule is basically an if-then statement, or it can be written as P, therefore Q, in which P is the antecedent and Q is the consequent. Each of the 4 cards represent the 4 possible premises. P, not P, Q, not Q. So P would be a vowel, not P would be a consonant, Q would be an even number, and not Q would be an odd number. Now, when presented with each of these premises, we can make inferences. These can be divided into two types of reasoning: inductive reasoning and deductive reasoning. Inductive reasoning is invalid, while deductive reasoning is valid. The first and most obvious is when presented with P, in this example the A card. Since the rule is P therefore Q, given P we can obviously deduce that Q must follow. This is known as affirming the antecedent, or modus ponens, which is a valid deductive form of reasoning. Next, when presented with not P, in this example the K card, we could infer not Q. This is known as denying the antecedent, which uses inductive reasoning and is therefore invalid. Just because you're presented with not P does not necessarily mean that not Q must follow. When presented with Q, people often infer P, but like I said, the rule only goes one way, so just because the rule is P therefore Q does not mean we can turn it around to say Q therefore P. This is known as affirming the consequent, which is another invalid form of reasoning. Now, finally, when presented with not Q, we can infer not P. This is often missed by participants of tasks like this, despite it being a valid logical form of reasoning known as denying the consequent, or modus tollens. This is valid because if we have not Q, the only logical conclusion would be not P. If we apply this to a real world example, we could say something like all tigers have stripes as our premise, then we could make inferences using both inductive and deductive reasoning. For example, if it's a tiger, it has stripes. If it's not a tiger, it doesn't have stripes. If it has stripes, it's a tiger. If it doesn't have stripes, it's not a tiger. Looking at the results of the card selection task, one might quickly jump to the conclusion that humans are not very good at reasoning and therefore illogical. But one important thing to note is that content is crucial to a task like this. Participants perform significantly better when presented with cards that have real-world applicable examples. This can be seen in a different form of the card selection task. This time, each card is represented by a person. On one side of the card is a drink in which that person is drinking, and on the other side is their age. Participants are presented with 4 cards and the following rule: if a person is drinking alcohol, they must be 18 years or older. The task is once again to turn over cards in order to determine whether or not the rule, or in this case the law, is being followed. In this case, 72% of people correctly predict that the cards beer and 16 must be turned over. The beer card has to be turned over to make sure the person drinking it is old enough. The water card is irrelevant since it doesn't matter what age the person is. The 25 card is also irrelevant since it doesn't matter whether they're drinking alcohol or not since they're over 18. And the 16 card must be turned over to make sure that person is not drinking alcohol. It's much easier for us to reason in tasks like this because we can actually apply it to real world scenarios. In terms of actual variables, this test is actually quantitatively identical to the first. The statement if a person is drinking alcohol they must be 18 years or over is just another if P then Q statement, where drinking alcohol is P and being 18 years or older is Q. The 4 cards also represent the same 4 premises as before: P, not P, Q, not Q. This also helps highlight why certain inferences are illogical. The most common wrong answer in the first task was the A and 2 cards, but as stated earlier, turning over the 2 card is illogical. The 2 card is representing the premise Q. In this real world example, representing the Q premise is the age 25 card, so it becomes more obvious why this is illogical. Just because a person is over 18 does not necessarily mean they're drinking alcohol, so no matter what they're drinking, they're not breaking the law, and therefore there's no need to turn over the card. So the rule P therefore Q cannot simply be turned around to Q therefore P. If a person is drinking alcohol they must be 18 years older cannot simply be turned around to if a person is over 18 they must be drinking alcohol. This is inductive reasoning and is therefore invalid. It's worth pointing out though, it's possible to be wrong using deductive reasoning, and vice versa, it's possible to arrive at a correct conclusion using inductive reasoning. Deductive reasoning is only as correct as its premise, so given an incorrect premise like all birds can fly, we could use modus tollens to logically deduce that if it can't fly, it's not a bird. This is obviously false because a penguin is a species of bird that can't fly. And if we return to our tiger example, if we see a tiger and say it has stripes, therefore it's a tiger, this is an invalid form of reasoning, yet we have arrived at a correct conclusion. In fact, inductive reasoning is actually incredibly useful and we use it on a daily basis with incredible accuracy. Some of the most obvious statements and assumptions we make are actually using inductive reasoning. Things as obvious as, the sun will rise tomorrow, or if I drop this coin, it will fall to the ground. These statements, though obvious, are actually using inductive reasoning. How do we really know the sun will rise tomorrow? Because it's risen every day of our life so far? But nothing that has happened in the past can guarantee what will happen in the future. We can only make predictions and increase the certainty of our predictions, but we can never guarantee outcomes. In fact, everything we know about the universe, we know through inductive reasoning. How do you think we get these premises in the first place? How do we know that all tigers have stripes? Through inductive reasoning. But there's no way to know for sure that all tigers have stripes. Maybe there's an undiscovered species of tiger in a jungle somewhere with no stripes. It's just that every tiger anyone has ever seen has had stripes, so we can say with a high degree of confidence that all tigers have stripes, but it's impossible to know for sure. In fact, according to the strictest rules of logic, it's impossible to know anything for sure. Through scientific research, we can only increase the likelihood that something is true, but can never actually confirm it. A famous philosophical quote states that nothing can be known, not even this. But just because something can't be known with 100% certainty, when all the scientific evidence points to something, any rational person would accept it as fact. So when it comes to reasoning, it's not just about logic, but also about common sense and rationality too. Thanks.
All right, and that is your logic lesson for the day. So now we're going to go back to talking about problem solving and the actual process of problem solving, what's involved in that. So there was a book that was originally written by a math teacher, Polya, in 1945. It's still in print. Actually, this cover that's on the slide here is from the most recent version of its printing, 2014. And this book was called How to Solve It. And it's considered a classic problem solving textbook. And so in this book, Polya described what he believed were the steps that needed to be taken in order to successfully problem solve. So the first step in solving a problem is to understand the problem. And if we kind of translate this into more cognitive psychology terms, we can think about it as the fact that we need to encode the statement of the problem into our working memory. And we need to do this in an accurate way. The second step that Polya suggested is that we need to devise a plan in order to begin the problem solving. So in other words, this is the time in which we begin to search our long-term memory for possible plans or strategies for accomplishing the goal. Next is we have to pick one of the plans or follow one of the strategies that we have pulled out of our long-term memory and follow through with it. And then finally, we need to look back and evaluate our progress that we've made toward the goal. And again, to sort of put this in more cognitive psychology terms, we need to do some self-monitoring or what is called metacognition. That is thinking about our thinking. So we need to be in an evaluative sort of self-reflective mode in order to see if what we have applied so far in the step-by-step process has actually helped us successfully solve a problem. And so as you can imagine, there can be errors and breakdowns at each step along the way that can either make the problem solving more difficult than it needs to be, or can actually stop us from solving the problem altogether. And so at the first step, the step where we have to encode the problem so that we can understand it. One possible problem or area of error has to do with the limits that are on the capacity of our working memory. So when the initial state, when the initial problem is translated into propositions, or sort of the steps that are needed to get to the goal, the number of these propositions or these steps that are created, they might actually exceed the capacity of our working memory. So it might actually just overwhelm our human abilities. And then this, of course, leads to information being lost. And so to avoid this, what we can do, what we very frequently do without even thinking about it, is we use the strategy of using paper and pencil to record the steps that we've tried out so far and the particular strategies that we've used. And it doesn't have to be paper and pencil, right? It could be you, writing notes on your computer. I often will kind of write notes to myself as I'm writing a paper, just kind of sort of providing, hey, I looked into this. This is why I included this source and not this one. I'm thinking about going into this other part of the argument in the next section. So that way it's like this extension, right, of my working memory. So this is a great way to work around the limits of our mind. And then another potential problem at this step of the problem solving process has to do with whether we've understood the problem correctly. And so this issue has to do with how we've gone about constructing a mental representation of the problem in our mind. And so there are a couple of things that need to happen during this. So when we're trying to understand a problem, we have to decide which information is the most relevant. So what's the most important? What's key to helping us solve the problem? And then once you've narrowed down on that, then you have to pay attention. You have to continue to focus on that information that you've selected. So our attention is critical because like we know, there are limits to our attention. And so we not only have to continue to attend to the information that we focus on, but we also have to filter out other distractions. So for instance, there was a study done by Bransford and Stein in 1984 where they gave participants a math word problem, and they asked them to record, to write down everything that they thought about, that they felt as they were trying to solve these problems. And the results of this showed that a lot of the students had negative thoughts pretty early on in the process of trying to solve these math word problems. And that the students who became distracted by these negative thoughts and negative feelings of like, oh my gosh, this sucks. Why did I sign up for this study? This is really hard. Oh, I hate math. They were more likely to become distracted from the task itself. So it shows that they were having difficulty filtering out these irrelevant thoughts, and that it was actually taking up more of their attentional resources and making it more difficult for them to actually pay attention to the problem that they were trying to solve in the first place. And another challenge is just, like I said, selecting the appropriate part of the problem to focus on. So really effective problem solvers, they read the description of a problem really, really carefully. They pay attention to, they particularly pay attention to any possible inconsistencies in the problem. And again, when you're presented with a problem, right, you often have to sift through the information and try to hang on to the most relevant information. So as you're reading through a paragraph, for example, you're sort of picking up different pieces and maybe holding on to them and saying, oh, this is really important, or sort of telling yourself, oh, this isn't as important. And so it's this very active, effortful sort of process. So speaking of logic puzzles, I have another puzzle for you all. Yay! So this is actually from a classic study in cognitive psychology on problem solving. And so the word problem is this. It says, 2 train stations are 50 miles apart. At 2 p.m. on Saturday afternoon, 2 trains start toward each other, one from each station. Just as the trains pull out of the stations, a bird springs into the air in front of the first train and flies ahead to the front of the second train. When the bird reaches the second train, it turns back and flies toward the first train. The bird continues to do this until the trains meet. If both trains travel at the rate of 25 miles per hour and the bird flies at 100 miles per hour, how many miles will the bird have flown before the trains meet? See, if I was given this problem and I was one of the participants in that previous study that I talked about, the Bransford and Stein study, where the students were having negative thoughts, I would be distracted by my negative thoughts being given this word problem.
Scores.
I think I have the answer.
Okay. What do you think, Sam?
So I think that the bird will fly 100 miles because it'll take, since they're 50 miles apart and they both travel at 25 miles per hour, that means they'll meet each other at an hour. And if the bird flies 100 miles in an hour, it'll fly 100 miles in that hour.
Wow, nice job, Sam. Yeah, I had to not only look up the answer to this, but spend some time trying to understand it. So what Sam has just demonstrated to us is the more productive way of solving this problem. So if you were like me when I first read this problem, you might have likely represented it in your mind as is the case in figure A here, where you're sort of picturing the bird flitting back and forth between the 2 trains. And so if the problem is presented in this certain way, right? If you're understanding this problem in terms of the focus should be on the bird to help you solve the problem, then the solution is going to be really difficult. So if you use this method of representing the problem, you might try to calculate how far the bird flew on its first flight, then its second, its third, its fourth, its fifth, and so on, and then add them all together, add all of those cumulative distances to try to solve the problem. So the less obvious, but the more productive way to do this is to do exactly what Sam did, and to focus on the trains and the distances, and not necessarily focus on what the bird is doing. So if we represent the problem in terms of the amount of time that the bird is taking to fly, then the solution is really straightforward, just like Sam said. So the 2 trains are 50 miles apart and they're approaching each other at a speed of 50 miles an hour. So we have 25 and 25. So it'll take about an hour for them to meet. And then if the bird is spending an hour flying, that means that the distance it flies is 100 miles. So again, this is just another example of the very first step of problem solving, right? We have to understand what the problem is asking of us. We have to focus on relevant information and ignore irrelevant information, including our own internal thoughts and states and feelings. So another in the next step of Polya's 4-step plan to problem solving, there are some other possibilities for error along the way as well. And so this can happen when we are beginning to access our long-term memory to try to think through possible strategies we've used in the past, or plans that we could use. And the main danger here is what are called unwarranted inferences. So essentially, problems that arise when we're essentially barking up the wrong tree, where we haven't made an inference correctly, whether that's because we might be missing information, right? We might be jumping to conclusions based on nothing or very few pieces of information. We might have incorrect information in our long-term memory that we're then retrieving and then acting on. And then in this case, if we have missing information, faulty information, or very little information, then our long-term memory is not going to be very helpful in accomplishing the goal of solving the problem. And so another problem can happen at this stage when if we know that there is a successful strategy. As is not the case in the first two bullet points, we might have the correct inferences. We might have previous information. We might have all of the things that we need at our disposal, but we might not be able to access it in our long-term memory because the cues that we have are not helping us right now. So any cues that are coming from our working memory as we're sort of sorting through this information, they might not do the trick in getting us to the correct piece of information that we need in our long-term memory. So the next step when we have to carry out the plan, errors can come in when there are a lot of steps for us to track, right? Which makes sense given the limits on our attentional resources, on our working memory. We're just trying to juggle too much. And because of that, we can start to miss out on certain steps. We might lose track of things. We also might have trouble and make some errors when the sequence of the actions that we have to take is really vague. So if we don't really have a good sense of, well, first I need to do this, then after that I need to do this. Now I can only do A if B happens. But if the sequencing of actions is like, well, I have a couple things and eventually I'll get to the goal, then we're also going to have a harder time and probably make more errors too, right? We don't have a very good detailed roadmap. And then finally, if a task is or a problem is a lot more time consuming for us, it also increases the likelihood that we're going to be making more errors, right? Again, sort of this limit to our energy and attentional resources. And then finally, at step 4, during the evaluation process, we need to be sure that we are examining the following. And sometimes this is where we make errors along the way as well, because we might not go back through and evaluate as thoroughly as we should. So in order to sort of thoroughly evaluate things, we need to ask questions like, well, did we actually achieve the goal that we set out to do? Did we take the appropriate actions, right? Did we follow all the rules in order to do it? Did we have a useful strategy that was also efficient? And also, is this a strategy that we should hold on to? Is this something that we think might come in handy in the future? So in the midst of sort of these more predictable errors, we also have some more predictable behaviors that people tend to demonstrate when they are trying to solve problems. And we've alluded to some of these and also talked about one of them, functional fixedness, but we'll kind of just review here. And so a common behavior that comes up with problem solving is what's called rigidity or mental set. And so this is when people fail to solve a problem because they focus on one perspective on the problem, or they try to use one strategy that they have used in the past that's been helpful. And so this can result, this rigidity, this sort of stuckness It can be the result of limited capacity, right? Maybe you're just crunched for time, or you're running on very little sleep, or you're really stressed out. And so when it comes to problem solving, your brain is just trying to think of shortcuts, short and sweet. Let's try to do the bare minimum because we don't have a lot of resources available to us right now. It can also, like I alluded to, be this over-reliance on our experiences. And this can be because maybe we might get cocky, kind of think, oh, well, I've figured this out before. So this is going to be the exact same thing. I'll just approach it the same way. Or it could be that you're really new to whatever solving the problem is. And you're like, well, all I have to go on is what I've done before, so I guess I'll try that. And so one specific type of rigidity that's been observed is what's called a response set. So it's when you're stuck in kind of using a go-to method, even though a better or a more efficient one actually exists. So kind of in comparison to the over-reliance on experience, when you're overly relying on your past experience, this is also in the context of not really knowing any other strategies. It's like, well, I have to just go with what I know. There isn't a way for me to try to come up with anything new. I'm just going to go with what I know. Versus in the response set, this is when you are using a go-to method, even though there is a better one or a more efficient one that exists that you could easily access. So an example of this is a woman who always cut her roasts in half before she put them in the oven. And when she was asked by her daughter why she did this, she just responded, well, that was how my mom always did it. And when the daughter asked the mom, well, why did grandma cut these things in half? It all fits in the oven. Mom was like, you know what? I don't actually know. The daughter pointed out, like, you could just put the whole thing in the oven. I don't know why you cut it in half. And so the daughter then asked the grandmother, why do you cut? I noticed that mom cuts roast in half, and she said she does it because of you. Why? And so the grandmother responded that, well, they just never had a pan that was large enough to fit the whole roast in its entirety. So they just always cut them in half. And so this type of rigidity shows that we are creatures of habit. We really do tend to do things in a more usual type of manner without really thinking about why we're doing that task in a particular way. And then finally, another type of rigidity that we've already talked about is what's called perceptual set. This is also called functional fixedness. So if you think back to the video that we watched last week, in which college students, they had to figure out how to tie two pieces of rope together using only a chair, an empty paint can, and a pair of pliers. And we saw that a lot of them were suffering from this sort of perceptual set. They were stuck thinking, well, a chair can only be a chair, pliers can only be pliers, like that's just an empty paint can. And they're not able to see that different objects can have different uses. And actually in that functional fixedness setup, when they were provided with both pliers and a paint can, they could have used either the pliers or the paint can to be the pendulum source, to be able to swing, get one of the ropes swinging, stand up on the chair, hold the other rope, grab it, and then tie it together. And so cognitive psychology, we can make sense of this sort of faulty approach and say that when we encode a word or a situation or a scene, what become activated are the most common uses or characteristics of an object. And then these, of course, can interfere with the process of coming up with new uses. We have these shortcuts and they're really great, except for when they're not great. So I'm going to start talking about problem-solving techniques in the few minutes that we have left. And then we will continue talking about problem-solving on Friday and hopefully finish that up. So we've talked about some of the errors that can come up when we're problem-solving, steps along the way that we should take in order to successfully problem-solve, some of the behaviors that we tend to default to because of the sort of cognitive shortcuts that we have. And some researchers started to look at what are some good go-to techniques in order to successfully problem solve. So how do we overcome the rigidity that can often come from response set, where you're like, well, this is always how I've done this, or perceptual set of like, well, this box of matches is just a box of matches. We need techniques to sort of help us break out of that rigidity and to be more creative, or to potentially use insight, right? Our top-down processing abilities in order to figure something out. And so one of the best techniques is being able to represent a problem really well. And if we represent a problem well, this really helps us to organize the information more effectively. It cuts down on that strain on our limited working memory. And so representing a problem, particularly if it's more abstract, right? So for example, like in the form of a word problem, these representations are usually done with symbols of some sort. So for example, there's this problem here. I always hated these in school. I wish that I had learned a little bit more about good problem solving techniques. But the word problem says, Mary is 10 years younger than twice Susan's age. 5 years from now, Mary will be 8 years older than Susan's age at that time. How old are Mary and Susan? So a way to go about this is to essentially define the things you're looking for. So we're looking for Mary's age, and we know that Mary is 10 years younger than twice Susan's age. So I have m equals 2s minus 10 to represent that. And then we also have the confusing sentence of 5 years from now, Mary will da 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 da. I have that represented as m plus 5 equals s plus 5 plus 8. So if we do some combining, and then if you go back to algebra where you're like, okay, you subtract this from this side and get this from that, you can eventually solve for both Susan's age and Mary's age. And so again, by assigning these symbols, by having representations of the concepts in this word problem, it becomes a lot more, a lot easier to try to solve this kind of problem, right? We don't have to hold all of this different information in our mind. We can just write it down. We can also be more organized. We have all the information we need to see. We can organize it visually. We can even label things if we wanted to. And then another way of representing problems is by using a matrix or matrices. This is actually a problem that I got. There was like this kids problem solving site that I found, and this was like one of the difficult ones. But you've likely heard these where you're having to figure out, who was doing what and is in what condition. Another popular one is, learning about people in the hospital and saying this person has tuberculosis, this person's in room 104, da 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 da, and figuring out where everybody goes. And then finally, some other ways in which we can represent problems well, which again is going along those lines, right, of sort of this symbolic representation that's helpful for us and is a way to extend our working memory capacity, is by visualizing things, whether that's, we're using a diagram or a graph to try to figure out something, or if we're using visual imagery, right? If you're a more visual sort of problem solver and processor, maybe you're drawing things out as you're trying to solve a problem. And so these are just some of the more common, the more tried and true techniques that people use in order to help them better problem solve. Okay, so I am aware of